Hey guys, how y'all doing? How is your day going? And it's just starting. How was your night? Hope you had or are having an amazing and a beautiful day today. For those of you who don't know this, my name is Praise, and I'm the one who will be taking you down the Python for the AI era series. This is video two. I don't know if at the start of every video you would want me to kind of like do a recap of what we did in the last video, or if I should just proceed. But in summary, the last video just was your under the hood of Python. So we covered everything from how your .py file is actually compiled to give you results. We went at length into how you go from the Lexa, how your tokens are generated, how you get your ASTs, how you then get your bit codes, and how it's now compiled through your VMs to give you a final output. We still touched on a bunch of other things, just mostly focusing on the basic things you need to know before you actually start coding. As we proceeded, we still did get introduced to your print statement and a bunch of other codes. We did intent, should I say, technical or practical representation of how Python handles parallelism and concurrency differently with the IO bound and CPU bound tasks, and we carried out some code examples, seeing how fast and how much time is saved when you do IO bounds casually and how you do IO bounds with threads or the threading model, and likewise for CPU bound operations using the multiprocessor model. So if you are brand new to coding, that might have been a bit much for you, but at least you understood the concept. If you're an OG developer, especially now that there's so much hate on the internet towards Python developers, like people are saying we're not all that, which is like they talking about people who write code in Python. They're not talking about Pythonistas, which is what we're trying to become. When it comes to Pythonistas, all them Java developers can say nothing. So either ways, if you're already an OG coder, or at least you know how to write codes in Python, this series is going to give you ways to improve your coding skills. It doesn't matter how basic the topic we're covering sounds like. Take, for example, the last video. It will show you how to create more advanced functions, not that ugly ass stuff that I'm coming off so aggressive. Before I started recording this video, I was literally on a call with a Java developer and we got into like a proper argument. And they tell me that Java runs models. We're like, do you really want to compare Java to Python? Anyways, this is a tutorial video. We're not here to debate who is better because we obviously know it's Python. So yeah, without further ado, let's get into today's video. So today we're shifting our mental model. We are moving away from surface level syntax and diving into the underlying C Python mechanics. So by the end of this video, you wouldn't just know what your code does, but why it does what it does. So every video I'm going to give you a roadmap of these. So our roadmap for this one is the object model, the numeric tower, the string API, and built-in toolkit. So we are now focusing more on coding. We're going to be writing a lot more codes in this video, understanding how to work with the different data types and so on and so forth. But we're still going to be lifting up the hood a little bit. I'm going to try and make this video as broken down as possible so that if this is your very first introduction to integers and strings, you're going to have a good enough understanding. But we're going to still pimp it up a bit so that even if this is your first time, when you're leaving, you're going to leave here more with more knowledge than someone who just googled it on the internet or whatever. Or if this isn't your first time, you're going to get more understanding as to why your code's been working the way it's been working. But yeah, without further ado, don't forget to like, subscribe. All the links which I would reference will be in the description. Any code which you may need to copy will be in the description. My GitHub, the book itself, which is what is pioneering this series, will be in the description. And any other resources I feel would be beneficial will be in the description. So don't forget to like, comment, share. It lets me know that you enjoy this video and you want to keep seeing more of this video. But yeah, let's get into it, shall we? Okay, so we're going to start with the object model. And one thing you should just keep behind at the back of your head is names are not boxes. The main difference between Python and other languages like C and Java comes down to the memory. So, other languages think about variables as literal physical boxes in memory permanently stamped with a specific type, which if you start learning programming with C, C++, they'll always tell you, like, that was a very common example they'll use. Think of your variable as a box. But in Python, names are not boxes. Variables in Python are like sticky notes. So they are name bindings that you attach to the object that is currently associated with whatever name the variable is. So the type belongs entirely to the object itself. So when you type, for example, x is equals to 5, Python creates an integer object 5 and slaps an X sticky note on it, or like a sticky note that has X written on it on the object 5. So each object consists of three fixed properties. You have the identity, which is the object's address in the memory. You have the type, which is the class it belongs to, whether it's an integer or a list. And you have the value, which is the actual data stored in the object. So, for example, if you have x equals to 42, if you want to get the identity, you just print ID x. If you want to get the type, you just print type x. So in Python, we also have something called assignment. So assignment is binding, it's not copying. So if you were to do y is equals to x, y actually becomes x. So it's not just copying the content of x and like placing it into y. You are saying whatever location x is pointed at, point y to that location. So I'm just going to pull up my computer so we can see a visual representation of that. Alright, so for this, I don't think we need to use a file. Let's just do this in our terminal. I'm trying to like drag this stuff up, but the line between the terminal start and my actual face is like blurred. Okay, so obviously we're going to start our Python terminal. Then we want to define. Let's just use a list and say a is equals to 1, 2, 3. Then we're going to say b is equals to a. Now, this isn't going to copy. There is a copy keyword we use if you want to just copy the content. But if we do b is equals to a, this now assigning b the exact location of a. So whatever change we now make to b, okay, let's just say 4, is allegedly supposed to work on a. So if we now print out a, is now going to print 1, 2, 3, and 4. So we can get, let's get the ID. So just going to do print the ID, we'll do of A, and let's get that of B. So you can see the exact same. But yeah, so Python gives us different ways to compare things. We have identity and equality. So in the previous example, A, that is if you use the double equal sign, so A equals to B and A is B are both true because they point to the same location which we confirmed when we checked the ID. But if we were to individually create and we'll say A is equals to 1, 2, 3, B is equals to 1, 2, 3. A equals to B is true because it checks the value, but A is B is going to be false because they no longer point to the exact same memory location. So what's the takeaway here? Almost always use equality for values and reserve identity for singletons like none, true, and false. This is crucial because CPython has something called integer interning. It's like a memory saving trick. So if you were to create a standalone integer and the value was, let's say, a is equals to 256 and b is equals to 256, not as least like as an integer, as long as it falls within the range of -5 to 256, Python doesn't create a new memory object for it. It just gives a or a reference to like a reserved pre-created value for those range. So if you use is and the if you use the identity and the equality to check it, the operator check it, both of them are going to be true, even though they were created as standalone integers. But once you try it for any number outside of this range, it's not going to work. All right, so we're moving on to the next section, which is the numeric tower, that is Python's maths engine. Python comes out of the box with 5 distinct numeric types. We have the complex, which is real plus imaginary numbers. We have float, which is the IEEE 754 precision. We have the decimal, which is exact base 10. We have fraction, which is exact rational. And we have int, which is arbitrary precision. So the infinite integer, unlike in C or Java where an integer has a strict size like a 64-bit hardware limit, Python integers have arbitrary precision. So you can think of it like an infinitely like stack of Lego blocks. You could just keep on stacking on them and stacking on them and stacking on them. They never overflow because Python dynamically allocates more memory to tack on more digits as your number grows. You are limited by nothing except your machine's physical RAM. So it stores a huge number as a list of giant digits. It uses base 2 raised to the power of 30. So that is from digit 0 to, I'll put the value on the screen here so you can see it. Instead of using like base 10, which is just digit 0 to 9. So Python is great for convenience. You never have to worry about your math breaking, but it's slow for heavy calculations. So I'll just switch my computer now so you can run a quick experiment. Okay, so the first thing we need to do is just import the sys model. Then we're going to use something called print sys dot get size of. So what this does is going to give us like it's going to give us the size of the numbers we're going to pass through it. So kind of like just testing the limits to see how much your values can go with Python. So we're obviously going to start with our print, and it's now going to be sys, which is the model, and we're going to be calling the get size of function. And inside it, you're now going to pass the value or the variable you want to get the size of. So let's just start with something simple. Let's do 0. Okay. Then let's step it up a bit and let's do, I don't know, let's do 2 exponent that is raised to the power of, let's say, 30. Then let's try a bit higher and do 2 raised to the power of 100. So as you just keep increasing the value, so yeah, you can see like how it just keeps growing. Even 0 doesn't use 0 bit. If you check for 0, what is just saying here is saying that 0 uses 28 bytes. That is the total size of bytes we're seeing. So what I was just saying there, for example, if you see 0 uses 28 bytes, so that is 24 bytes of overhead and a default by 4 bytes padding. Then if we check for the 2 raised to the power of 30, if you multiply that, that's going to give us like 6 figures. So if you say the number of 4 byte digits we have there, there are 2 digits, and the total of bytes is 32. So that is like the exact boundary where it overflows. Because if you check for like the value of what I said Python uses to store, I said it stores uses base 2 raised to the power of 30. So that is literally what we did here. So that is might not be like an exact value, but basically it is. Then we did 2 raised power of 100. So that is a 31 digit decimal number, which is the number of 4 byte digits is going to have, in this case, going to be like 4 digits, and the total size of bytes is now 40. So there's a whole match you can do to understand that. But yeah, if you want to even go to higher numbers, you can keep raising up the number as much as you want, as long as your CPU is going to be able to carry it. You've got nothing to really worry about. And next, we're going to talk about flexible bases in Python. So you can write numbers in different bases like binary, octo, or hexadecimal, and so forth. Python reads these prefixes automatically if you use it's like string. But inside your integer, you'd pass in a string and then you pass in like a zero. So when you do that, you can put the base before you now put the value within the string. Unlike other programming languages that assume int is in base 10, in Python, as long as you set the second argument base to zero, this tells Python to auto detect the number system based on the prefix of the string. So I'm just going to show you an example here on the screen. But we'd have usually, obviously, you call your int. Within it, you're going to have your base. So if it's for binary, you have like 0 and B. If it's for octodecimal, is it octodecimal? You call it an octo. You have 0 and O. If it's hex, you have 0 and X. And if it's decimal, you really don't need to pass anything. You just put in your value, then you'd have your comma, and you'd have the zero. So the first two digits is usually to just say this is the base I'm writing in. The second one is the actual value irrespective of that base. So if let's say I pass 0b for my first value, for my first of the prefix of the string, I cannot have something like 110, 010. Then I would close the string, have a comma, and then I'm going to pass the zero, which is not going to let them know to detect the base in the string. Another way you could do this is to just write the value, then the base. So you just pass integer, then you have a string where you pass the value. Let's say for a hex, we'll pass like FF, and then you'd have a comma. And instead of just putting zero there, you now put the value of the base. So hexadecimal in this case would be 16. Then readability in Python. So Python uses something called underscores. I feel everybody knows underscores if you've been on social media long enough. So let's say if you have a large number like a million and you want to write them down, you can just use underscores to separate like all the space where you put commas, because Python ignores these underscores. So if let's say you did 1_000_0_000, it's just to Python going to read as if the underscores are not there, but for you it's going to make it easier to read the numbers, especially if you are not good with like if you give me a large number to read and there's no commas, I would be counting that over and over again. I'm not the best with it. Now we're done with integers, we're just going to jump over to floats. So whilst Python's integer can grow forever, its float is bound by the hardware's physical limit. Every Python float is a 64-bit IEEE 754 double precision number. This format is incredibly powerful, but comes with something called floating point ghost that every developer must understand. So a float is divided into three parts to balance range and precision. So you first have the sign, which is usually 1 bit. This is the number. This it just says if the number is positive or negative. You have the exponent, which can be 8 or 11 bits. This controls the scale. So how large or how small is the number? Then you have the mantissa or the significand. So this is usually like 23 or 52 bits. This controls the precision, that is the actual digit. But whilst we're here, let's ask a very popular question. Why is 0.1 plus 0.2 not equal to 0.3? This because every Python float is locked into the IEEE 754, like I said, double precision format. So since the mantissa, this where the digits are stored, is only 52 bits, just as you have like a fraction 1/3, if you turn that into decimal in base 10, it repeats itself over and over and over again. 0.12 repeats infinitely in binary. So since you're only working with 52 bits, once the that has been maxed out, the rest of the value gets cut off. So if you had like zeros and zeros and zeros, and maybe the last value was 3, all this usually gets cut off. So if you are dealing with something like money or something that is like precision required, you usually use like, you want to stay away from float, use something called the decimal model. We're going to touch on this a little bit later, but this, because it stores in base 10, it's not converting it to binary. So if you pass 0. 0.1, 0.1 is 0.1. It's not going to keep repeating itself. You also never want to use the equality with float. If you want to check if values are equal for float, you use a math function called math dot is close. This is just going to check if two numbers are close enough within a tiny margin of error. Then in float we got something called special values and nothing number. So this are states for like mathematical edge cases. So you have the infinity, which is your float, comma, INF of negative INF. So this just represents values beyond the computer's capacity. So you can like get using sys dot float underscore info dot max. Then you have the naughty number, which I feel a lot of people have come across. If you ever come across program where you saw like NAN, that is not a number. So it's just used for undefined operations. So the NaN paradox, NaN is never equal to NaN. So if you ever do NaN equal to like the equity equal to NaN, it's always going to be false. So this was done by design in the IEEE spec. So if you want to ever check if both NaN values are equal, I guess, you'd want to use another math function called math dot is NaN x to do that. So next we'll just go into decimals. Okay, so since math isn't precise enough, in float, Python provides the decimal types. So this is the most critical rule when using the decimal type. You never want to initialize it um like without a string, so just passing the value like that. So if you were to say do decimal parenthesis 0.1, it's going to pass that as a float, which is like it defeats the whole point. We're trying to ensure it reads it as a base 10 value, so you pass decimal. But instead of now passing just the actual value like that, you pass as a string, so you enclose it in your inverted comma. This will now tell Python to read each of the values individually. So it will read 0, it will read the point, it will read the 1. That's why if you pass 0.1, it's going to be 0.1. Then when you're working with flow, like one of the best times to use decimal is when you're maybe building a financial related app. But there's something that is really tricky with the decimal number. We have this stuff called the quantize method. So they have the ability to handle various modes of like rounding up values mathematically. So before we start, there are a few things we want to import. So there are multiple ways we can do an import. You can either just say we can do import decimal. This will import the full decimal model. If we don't want to be always typing like decimal dots when we're using the, so and we just want to type the function's name from the decimal stuff, which is not really advised, you say import decimal as asterisk. So if you are calling any model, any function from the decimal model, you just type the name. But if you want to be more specific, maybe it's not every single thing you want to use, you just say, especially since like some models usually have files with the same name, you can just say from decimal import. So the first thing we want to import is obviously the decimal model. This is what we're going to use to create decimals. Then we want to import get context. Then for the stops we want to round, maybe we'll just work with two. So we'll do round half or and round half even. These all in capital letters. So the first thing we're going to test out, should I have done this in the terminal so we can just listen the output immediately? Let's move to the terminal here so we'll just see the output of everything we're doing immediately. Okay, so the first thing I said you should ensure you don't do defining decimal values without a string. So if we were to do 0.1 without a string, so you can see 0.1 has so many other integers that come after it. But if we were to do this and actually wrap it in an inverted comma, zero point 0.1 is zero point 0.1. But if you did want, or maybe you were working with like division and stuff, and you want to define the exact amount of digits you want to get, kind of like, when you're rounding up and you want to say like dot 12 if you work with strings. So we're going to use this get context function. So get context, and then we're just going to say maybe how many numbers do you want, how many position numbers you want after. We can, let's do 10, I guess. So now we are going to do division, and we're not going to look inside the string so we can get excess values. So say decimal, and we're going to divide it by. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So if we decide I want to increase this again to 15, you can see the number gets longer, and we can even do it to 50, and it just keeps growing. It's just kind of like setting a fixed point of max amount of values we want to show after the decimal. For the rounding, so we're just going to define a variable, and this is going to be a decimal which we're going to call in a string. So we need to give us something so we'll be able to round it off and see. So when you're working with the method, we're going to use quantize. So it's just going to be price dot quantize, and then we're going to be like, what are we rounding it up against? Okay, so I feel that is briefing enough. If you are enjoying the video so far and want to get access to more of our detailed resources and learn more on this topic and many other topics, I would advise you check out the book which was created for this specific series. It's called Python for the AI Era. The links to download the book will be in the description below. Don't forget to download, rate it, and share it with your friends. I promise there is so much more to learn in the book, most of which we'll cover here, but still so many things that the book will cover at length. Feel free to use both resources to learn. You can never learn too much now, can you? Alright, so next up we're going into strings. So Python strings are a lot more than just a list of characters. They are a sophisticated implementation of the Unicode standard designed to handle global text seamlessly. So in Python, strings are immutable sequences of Unicode points. Unicode points, those are just like unique numbers assigned to every single characters in existence, ranging from 0 to, like, I'll put the value on the screen, is like 1 million plus. Because it uses code points, Python can natively display emojis, mathematical symbols, and diverse human languages without special conversions. So just look at a simple table of what strings versus bytes. So we'll be comparing it against features, that's the content, the usage, and the conversion. So strings are obviously human text, while bytes are binary data. So for content, they are a sequence of Unicode points, while bytes are a sequence of raw 8-bit values. So that's from 0 to 255. Then the usage is usually in UI, business logic, text processing, while bytes is like network packets, file storage, and images. Conversion, so you use dot encode to become bytes, and you use dot decode to convert bytes back to text. Then we have literals and escape sequences in Python. So Python provides various ways to define strings depending on your needs. So you obviously have the literal type, so you have the single or double quote, you have the triple quote, which you usually find inside functions but not required. They are mostly used for like doc strings. Then you have the raw strings, that's where you have an before you have your inverted comma. So this just allows you to work with backslashes like as literal characters. So it's essential when you're defining paths like locations of to where a file is stored in your device. We have F string, which is one of my favorites. This allows you to embed variables and expressions directly inside your strings using curly braces. If you paid attention to the last video I did use a lot of strings. Then we have some important escapes. So escape sequence just allow you to insert characters that are otherwise hard to type. We have the basic ones like slash n, which is to jump to a new line. So as you're writing within your string, you can just add slash n and still continue writing within that string. But when you print it to the terminal, it's going to like start the next one coming after it in a new line. You have slash t for tab. You have double slash, which just allows you to put a backslash into your system. You have Unicode by name. So if you use backslash n and you type the name, it will allow you to find characters by their official description. So you can just go on the internet and find what all the Unicode names are. Like slash n, then if you put grinning face, that's just going to put like the emoji. You have Unicode by X, almost the same thing, but you do slash U, and you can either use the 4 digits or that. So if you do small U, that's the 4 digits ones, and if you do like a capital U, that is the 8 digits one. So you just for specific hex values. So now we're just going to look into some string methods. These are just things that allow you to carry out certain types of actions on your strings. Before we continue, let's take a minute to thank our sponsors for this video. Our sponsors are the reason why we're able to bring this detailed series to you for free. Our first sponsor is Vultrin. We spend so much of our time securing our code, our databases, and our digital infrastructure, but we rarely think about the actual physical infrastructures keeping us safe when we step away from our decks and move through the real world. That is exactly why Vultrin was built. Vultrin isn't just a simple safety app, it's an uncompromising zero-knowledge personal protection ecosystem engineered for zero failure performance. When you trigger an alert, Vultrin's network routes your emergency data with minimal dispatch latency. So if you're commuting late, or traveling through unfamiliar areas, proactive features like Safe Walk and the automated deadman switch actively monitor your progress. If a crisis occurs, the system automatically activates a localized evidence vault, capturing and locking ambient logs behind encrypted databases so that your data remains tamper-proof and completely your own. Do not leave your personal physical security to chance. Build a reliable safety architecture for your everyday life. Go to Vultrin.com right now and secure your world. That is VAULTRYN.com and secure your world because your safety is non-negotiable. I would also like to thank our second sponsor, Techinovum. In the modern technology landscape, the gap between having a visionary product concept and deploying a robust, high-performance platform is massive. Most companies fail not due to lack of ideas, but due to a failure in architectural execution. That is what Technovum tries to solve. They are an elite technology and engineering firm dedicated to transforming complex challenges into highly scalable, enterprise-ready digital ecosystems. From deep technical system architecture and production-ready machine learning pipelines to building complex consumer-facing mobile platforms, Technovum designs softwares for the AI era. They don't just build application, they engineer the underlying structural infrastructure that allows your software to operate at maximum efficiency, scale seamlessly under load, and withstand rigorous security standards. Their engineering framework is optimized for performance, speed, and uncompromising reliability. Stop letting technical bottlenecks slow down your market delivery. Partner with a technical powerhouse that builds for the future. Visit technovum.com.ng today and let them engineer your next breakthrough. That is techinovom.com.ng. Now back to the video. Okay, so we're going to just be working with a bunch of string methods. So before we start, we'll just define the string which we're going to be using for most of what we're going to be doing. We're just going to have everyone's favorite hello world. Okay, and we'll just define a little list. Once we use it, you see why we're doing that. I just want to go and get out of the way first. So we're going to have Python, we're going to have is and fast. Okay. So I'm kind of like grouped all the different methods which we're going to be working into different categories. So the first one is case conversion. This one almost everybody knows. So we'll start with s dot lower, which is to just convert every single thing to lowercase. Now, when you're working with functions, you must always make sure to do parentheses. If you don't, it's not really going to call the function. It will just show you the location of where the function is at. So you have to call it with parentheses, and it's going to convert everything to lowercase. You can also do dot upper to convert everything to capital letters. You can do dot title, just capitalize every single first word. You can do swap cases. So for the ones that are small letter, it will make them capital. The ones that are capital will make them small letter. Okay. Which other one do we have? You can do case fold. So you usually find yourself using case fold when you start working with, like, I guess non-English characters. I think that's like, it's very similar to lower, but it's more aggressive. So have case fold. And yeah, let's go to the next category, which is stripping. So this is to just remove like white spaces and whatnot. So you can see the one we're working with has a bunch of white space at the front. So if you just, let's say we were to do s dot strip, let me redo s and have white spaces at both the front and the back. Okay. So if we were to do s dot strip, you usually find yourself using this more when you start working with users input. Sometimes users might type and be putting random spaces, and those spaces might cause an error, especially when you're working with things that the value has to be precise. So you usually want to, like, passwords, you'd usually want to like do strip to ensure no extra white space is being added. So it's going to remove the white space from both ends. I redefined s, I removed the capsule, the space in front, which was uh, but so yeah, if we do strip, it's going to remove it from both ends. Then if you want to just remove it from the left hand side, you just do l strip. If you want to just remove it from the right hand side, you do, I guess, r strip. So if you want to remove specific characters, you actually pass arguments into the parentheses. So you have s dot strip, we have these parentheses which we're calling. So now we're not going to pass what we want to strip from our, sorry, my bad. The next category we have is searching. So you just use this if you want to find certain words within your strings. So we can have s dot find. So you're not going to pass the exact word you're looking for. It will give you the very first index where it was found at. So in Python your indexing starts at 0, 1, 2, 3, 4, 5, 6, 7, then 8. This is obviously including all the white spaces. So the word started at the 8th index. So this s find, you also have something for like s dot index. It's similar to find. The only difference is now when it comes to error handling. So if you are using find and you search for a word that doesn't exist, it's not going to raise an error. But if you are using index and you do search for something that doesn't exist, you're going to get a value error. So you can either manually handle that error yourself, or you could just use find to do that, and if you just get a negative one, that means it wasn't found. So if you want to count the amount of time that something occurred, you just use s.count, and you can now put what you're trying to see, how many times it occurred in your string. It'll give you the total count it occurred. If you want to find if it starts with, you can just do s.start with. So these ones are boolean responses you get. So we want to check if it starts with H. So it's going to give us false obvi because our S starts with white spaces. So now it's going to give us true. You can do the same thing for ends with. So now your programming languages would practically be useless without arithmetics. Those are things that allow you to carry out different actions on your um program. So we're going to just touch on some of the arithmetics. There are different categories, so we'll just group them and address them in their groups. And down the line, when we start going further, we'll see how we can use them in more advanced terms, if you may. So the very first group we have is our basic arithmetics. If you've done basic mathematics in like primary and high school, you will be familiar with some of this already. So we're just going to open up our Python terminal, and we're going to start. I guess the very first one you want to work with is addition. There's nothing special there. If you have two, you just use your add sign and whatever number. So 5 plus 2 is obviously 7. Likewise, if you have 7, you want to do subtraction, you just subtract it from whatever number you're subtracting from it. Another common one everyone knows is multiplication. But in Python, your multiplication sign is your asterisk. So you just put your asterisk and it's multiplied. Now for division, we have, oh wait, let's do exponentiation. Exponentiation is just raised to the power. So if you want to do 2 raised to the power of, instead of that, like this stuff, I think this is the sign here, this stuff, instead of this, we're going to use our asterisk again, but twice or double of it. So 2 raised to the power of 3, that is 2 times 2 times 2. And now for the division, so we have our normal division which performs float division. So if you just have 6 divided by, sorry, 2, that's going to give us 3.0, and the value is going to be in a float. Then let's do 7 divided by 2. That we usually have a remainder. Then another type of division we have is our floor division. So what this does is it divides, then it rounds down to the nearest integer, most likely towards the negative infinity, not towards 0. So if you have 17, floor division is just this but double. So if you have 17 divided by 5, you're going to get 3. But if you have negative 17, what am I typing? If you have negative 17 divided by 5, it's going to give us a negative 4 because negative 4 is lower than negative 3.4. So next we have modulo. This returns the remainder. So if we have a number that's going to give us a remainder, let's do 7. The modulo is the percentage sign. Where's my, okay, modulo 2 is just going to return the remainder instead of returning the actual value. So you usually see yourself doing this. Maybe a very basic example can be if you want to get if you want to find like all the even numbers, you can just do if the modulo of that number against 2 is 0, then it's an even number. That is like a very basic example you can try it with. But we have something called div mod, which will return the quotient and the remainder. So we can just have quotient and we can have remainder, and we can say it's going to be equals to div mod, and we're going to have the values we want. 17 and 5. Then we can print Q and we can print R. All right. I think these are all the these were all the basic ones we have. Next, we have the comparison of the relational operators. So these are just used when you want to compare values. It's always going to return a boolean that is either true or false. So you have your equality, that is your equal to. We've already touched on this multiple times. So we can say is 2 equal to 4. We can say is 2 equals to 2. Then we have not equals to. So you can say 2 is not, so that is the exclamation mark, equal to 4 is going to return. Did I indent? Where did I indent? Oops. So it's going to say 2 not equals to 4. Then we have greater than or less than. So we can say 2 is greater than 4. We can say 2 is less than 4. We have greater than or equals to. So 2 is less than or equal to 4. 2 is greater than or equal to 4. Then we have our logical and membership operators. These are just used for more high level logical flows and sequence checking. So you have and or not. If you remember logic gates from school, you may be a bit more familiar to this. So and is going to return true if both statements are true, or is going to return true if at least one of the statements is true. Not is going to return the reverse of the boolean you have. So if you had true, you're going to get false. If you had false, you're going to get true. Then in returns true if the value you're looking for exists in whatever sequence you're working with, whether it's a string, a list, a tuple, a dictionary. And not in is going to return true if the value you're looking for doesn't exist in the sequence. Then we have identity operators. This just check if two names refer to the same. We've already done this. If they refer to the same object in memory when we're comparing like um with against equality. So we have is and is not. So is going to return true if both variables point to the same memory address. Then is not is going to return true if they do not point to the same memory address. Then one of my favorites, we have bitwise operators. So these just treat integers as strings of binary bits. Those are zeros and ones. So we have and, but in logical, when you're doing and you're typing out and like this, we're going to go into this when we start going into conditional operators. But when you're dealing with bitwise, I think I've forgotten how my keyboard works. You're going to use this. So this is for and. So it's going to set your bits to 1 only if both corresponding bits are 1. I feel like I should put like a logic gates table thing on the screen so you can see it. Then or is going to be this one here. It's going to return, it's still the exact same way. It's going to reset the bit to 1 if at least one corresponding bit is 1. So you can have 1, you can have 0, but you're still going to get a 1 because at least one is present. Then you have XOR. So that stuff you usually use as raised to power in other operators is what we use as XOR here. This sets the bits to 1 only if the corresponding bits are different. Then you have not. This is this one here. Not, it just inverts all the bits. So changes 1 to 0, changes 0 to 1. And now we have shifting. So I'm going to go into shifting. I feel we should move to a board because we're going to do a little mathematics here. It's nothing serious, it's not complicated, it's basic math, I guess. So let's go into bitwise shifting. Inside the computer, numbers are just a line of ones and zeros sitting on a conveyor belt. So, because computers use binary, every position on that belt represents a power of 2. So you have 1, 2, 4, 8, 16, and so forth. So if you move to the left, which is left shifting, when you push when you push everything that's towards the left, every number moves into a higher position. So the 2 will become a 4, the 4 will become an 8. So you are doubling the value. Then if you push everything towards the right, every number moves into a lower position. So the 8 will become a 4, the 4 will become a 2. This results in halving the value. So the question will be like, why would you now do this instead of carrying out normal addition, multiplication, instead of carrying out number multiplication and division on like you would on a calculator? So if you use your calculator to do, for example, 12 times 2 or 12 divided by 2, it works, it's quite seamless. But the CPU is a bit lazier than that. So doing a full multiplication will involve complex logic gates and multiple steps of electricity flowing through the chip. A shift is just rewiring, nothing is being calculated, the bits are being moved over one slot. It happens at the speed of the electricity itself, making it hyper fast. So when you this is my seem more far like positive numbers related, but when you are handling negative numbers, you have something the tools complement. So to keep track of the negative numbers, computer reserve the first bit as a sign bit. If the first bit is a 1, the number is negative. So when shifting a negative number to the right, the computer is smart enough to keep the first bit as a 1 so that the number stays negative. It's like the conveyor belt is just going to remember the sign of the number while it slides along, which by default would then mean that positive numbers are 0. So we're just going to do a little calculation. It's nothing too serious, just a little math, so you can just see a visual representation of what is going to be happening in the computer. Okay, so we're going to start with the left shift operator, which is going to become like multiplying the number by 2 raised to the power of n, where n is the magnitude. So we'll usually have a left shift n. So a is the value, n is the magnitude. So if we had 3 left shift 1, so we're doing 3 multiplying 3 by 2 raised to the power of 1. So since this is a binary operation, the first thing I want to do is convert 3 into its binary value. So the new value of a is now going to be 0, 1, 1. Then if we're moving it by 1 by, so if we want to shift this to the left, what we're going to do, so we're just going to imagine like these are the positions, the way you have the tens, the hundreds in normal decimal math. We're going to have 8, 4, 2, and 1. So this is just going to be a table. Then on this table, we're going to have the value of 3, which is 1, 1, 0, 0. So if you want to shift this by 1, what I'm just going to do is just push all the values forward. So this 0 is going to come here, we'll have 0. The 1 will come here, we'll have 1. This one will come here, we'll have 1. And then we're going to now add a new value to the back, which is going to now be 0. So if you now convert this to decimal, the new value of this is now going to be 6. I don't know if that explained it to you. That is basically what is just happening. It's just moving it from its current placement to a higher one for left shifting. Right shifting is the inverse of that. So for right shifting, let's say we have 12 and 1. So 1 is our magnitude, 12 is our value. The very first thing you want to do, obviously, is converting 12 to binary. So if you convert 12 to binary, that's just going to be 1, 1, 0, 0. So if we draw our table again, we have 8, we have 4, we have 2, we have 1. So we're just going to have 1 1 0 0. So for right shifting, we're moving towards the right, which is going to half the value. So this 0 is going to come here. This one is going to come here. This one is going to come here. We can just add another 0 in front of it. So this will now be a new value, which is now going to be the value of a 6. Okay, now for our project for this video, we're going to be building a personal finance calculator. So we're just going to do a CLI personal finance calculator that takes income and expense data, performs calculations, and prints a formatted monthly summary using only the concept we've learned so far. So you need to define the variable for the monthly income like salary, freelance, and others, an expense like rent, food, transport, utilities, entertainment, savings. Then use type annotations on all variables. You want to calculate the total income, the total expense, the net savings rate percent, and use comparison operators to categorize excellent for savings that are greater than 20%, good for 10 to 20%, needs work for less than 10%. Then format all amounts as naira, or you can use whatever currency you use in your country. Then use an F-string alignment to produce a right aligned summary table using only standard Python, no external libraries. Add input validation. If the income is 0 or negative, print a clear error message and exit using sys.exit1. Check if expense is non-negative. Add a savings goal calculator. Ask the user for a goal amount, e.g. 500k, and print how many months at the current saving rate required to reach it. Then bonus challenge, you can add a 12-month projection table to print the cumulative savings at the end of each month, formatted with the full month name and a running total column. I'll show a sample output on the screen here for you. But yeah, I'm also going to provide you with a link for where you can submit, to make sure you push it to a public repo and just comment your link here so that we can all see it and I can see it. And thank you guys for watching. Don't forget to like, subscribe, share. The link to all our sponsors will be in the description. The link to the book is also in the description. The link to all my socials are in the description. And I can't wait to see you guys in the next video. The next video too is going to be a whole topic. We're finally going into control flow. So we're going to start doing more advanced stuffs, less of me talking, more coding. And let me know in the comment section below, is Python the best programming language out there? If your answer is not yes, then see you guys in the next video. Bye guys.